We've been working on linearity in two parts, the additivity property and the homogeneity property, for a long time with two vectors as inputs and two vectors as outputs, sometimes two. It's time to use other vectors like functions. Okay, so I'm going to say I is a function that takes in functions and gives out the integral of that function over the interval 0 to 1. Okay, in particular, I takes in functions that take a real number to the real numbers, right? So f here takes a single real number to a single real number. And then I'll pick two functions. I'll pick x and x squared. I think of those as like x and y over here when I'm thinking of additivity, right? X vector and y vector are then the functions x and x squared. Now, my pen is dying. I'm going to buy a new one on my lunch break here. But the integral of the sum of those two functions is, well, we got to evaluate that antiderivative between 0 and 1, and that just gives 1/2 plus 1/3. I'll leave it like that. I know I could simplify, but I'll leave it like that. And I of x plus I of x squared. That is I taking in one of the vectors plus I taking in the other vector. That is the integral from 0 to 1 of x dx plus the integral from 0 to 1 of x squared dx. And you know what? I think I don't even need to do this part where I write down evaluated between. I know that this is 1/2 and that this is 1/3. This is 1/2 and this is 1/3. Okay, so give me a second to draw a picture for you. Okay, so in black over here, I've drawn the graph of the function x. So it is also the solution set to the algebraic equation y is equal to x, just this nice line with the slope of 1. And I've labeled it x. And here I've drawn part of that parabola that is the graph of the function x squared. Okay, and those are the two things that I would call the vector x and the vector y in blue. And again, I hope those colors are coming through. And I'll draw the image of them under this function I. I takes x to 1/2 and I takes x squared to 1/3. Well, that's slightly less, so here's 1/3, and here is I of x squared. Okay, now, I was supposed to draw in green something else, the sum of the two vectors, so let me do that. I'm going to take a pause. Okay, I thought about it for a second. I need to draw x plus x squared. Now, let's think about it. What does x plus x squared assign to? Say 1. It assigns 2, doesn't it? Right, the height of the blue curve plus the height of the black curve. So 2, and that would be, I guess about up there somewhere. And everywhere in between, actually, I should add the height of the blue curve to the height of the black curve to get some new curve. That looks about like this. And indeed, that is a parabola there. And it needs to, let's see, this actually is equal to x times 1 plus x. So this has an x-intercept at 0 and another one at -1, so way off over there. Right, this would come down and it would have an intercept over there somewhere. But I'm really only interested in that function in the interval 0 to 1. Well, what does that get taken to by I? I takes x plus x squared, and it gives, let's see, let's actually do the arithmetic. This is 3/6 plus 2/6, and that's 5/6. Okay, 5/6. And then over here at 5/6, about there, I will draw a vector that is the output of I when you put in x plus x squared. Okay, and we get the same thing when we sum I of x and I of x squared. So in red, I put yet another vector usual thing of making that vector a bit longer, the head of the vector a little bit longer, that is, where do I put it? I of x, plus I of x squared. So you see the same kind of picture, but certainly the way that we draw these vectors, in the case these vectors are real valued functions of a single real variable, the way that we draw them is quite a bit different than the way that we draw vectors, right? Well, let me finish off the general proof that this thing is additive before giving you a glimpse of the similarity between this kind of function and vectors, as in n vectors. Okay, so I've now written in the part that shows that this function, is additive. For arbitrary functions f and g, I really ought to say that arbitrary functions f and g whose domain and codomain are both the real numbers. I of f plus g is the integral from 0 to 1 of f plus g dx, and you know that you can distribute integration over terms, so that's this, right? Integral of f plus the integral of g. Keep in mind these are definite integrals from 0 to 1. And of course this first term is I of f and the second term is I of g, and so we see that I is additive. The function that turns functions into real numbers, the integral from 0 to 1, is additive. And you're probably, I'm hoping, that you're looking at all of this and thinking, man, that guy needs to stop because his pen is completely dead. No, that's not that. You're probably thinking, this is a weird way to draw functions like the graph of a function in two-dimensional space as compared to the vectors that we were drawing before. Take 31a that we did before. Right? We also draw two-component vectors in two space. Well, is that you always draw things in two space? No. Let me show you the similarity. Give me a second to make a drawing. I'll be right back. I'm back. And I was talking about 31a where we had these vectors 1, 2, and 2, 1. And what I'm going to do is I'm going to draw those two vectors that are called x and y here in a completely different way. Okay? That completely different way is going to look more like the graph of a function. In particular, instead of drawing an arrow, what I'm going to do is I'm going to draw this. This is at 1 and this is at 2, and I hope very badly that you can see that this pair of dots is in blue and the other pair of dots is in black. In particular, I want to have two things here. I want to have x vector, which is the function 1, 2. That is, x assigns to the number 1, and x assigns to the number 2, the number 2. What do I mean by assigns to the number 2? I mean the second slot is 2, so it assigns to the number 2, 2. And I'm also going to draw on there the vector y, which is 2, 1. And that means the first component is 2, so y assigns to the number 1, the first slot, 2, and assigns to the second slot 1. So this blue pair of dots is a visual representation of y, and the black pair of dots is a visual representation of x, and it's totally unlike the arrow representation. Now let's think about why that is like the way that we talk about visualizations of functions, that is graphs. Okay, here are our two functions again. Well, how do I write this? This time we have the vector x, which is the function x. Okay, now if I were going to write that as a stack of numbers, how would I do it? I would say that x assigns to the number 1, the number 1. So in the first slot, I put a 1. And then what does x assign to anything else? X assigns to 1/2 the number 1/2. So in the 1/2th slot, I'd have to have a 1/2. And x assigns to the 3/2 slot 3/2. But you know what? There's infinitely many components of this vector. Right, that's why we call it x. The xth component of this, though, and half component is 1/2. The x component is x. The pi-th component is pi. There are infinitely many components of this. It's a stupid vector to write. All right, so the idea is that up here you say that x is a vector whose ith component is I, while y is a component whose ith component, vector y is a vector whose ith component is 3 minus I. See, that way the first component is 3 minus 1, and the second component is 3 minus 2. So this is a function, but it's x and y here are functions whose domain are just the numbers 1 and 2. Okay, so I only takes on the value of 1 and 2, whereas down here you can take on any value. And similarly, the vector y, that should be x squared. We just denote it as x squared, but it assigns to 1, 1. It assigns to 1/2, 1/4. And it assigns to 3/2, 9/4. And there's infinitely many components of it, so it's a really dumb thing to try to draw. But it's an analogy to y up there, right? So this vector, y squared, it's kind of a stack of numbers, but it's a stack of infinitely many numbers. So in both of these pictures, we can say that we go from a graph of a function. Perhaps the best way to think of a vector, a visual representation of a vector, is as a graph that's kind of a unifying picture to the number line. And I'll say that this picture right here goes with 31a, and this picture right here with 35a. Okay. And you can put in, well, let's see, for 31a, this picture to the right of that picture, put it in over here. And for 35a, put in this picture